Assalamu alaikum. Bismillahir Rahmanir Rahim. I welcome you to the 33rd lecture for the series of lectures on advanced computer architecture. Today, after a brief review of what we discussed last time, I will be discussing the strategies used for virtual memory address translation and the protection of multiple processors sharing the memory. And then at the end, we will discuss how the virtual memory performance can be enhanced by using these different techniques. Last time, we discussed the main memory organization and its impact on the performance of computers. Here, we noticed that the main memory is internally organized as banks of memory arrays and is normally packed in dual inline memory module, which is written as DIMM. Then we discussed different versions of DRAM used to enhance the performance of computer. These versions include fast page memory, synchronous and double data rate DRAMs. The fast page mode optimizes sequential access by exploiting the row buffer, whereas we found that the synchronous DRAM avoids need for handshaking between chips and memory controller, and the double data rate DRAM transmits data from chip on both the falling as well as the rising edges of the clock. Then we discussed the matrices used to measure the performance of main memory. These matrices include the latency and bandwidth. The latency of memory is mainly concern of the caches, whereas the bandwidth is having its impact on the performance of input-output and multiprocesses. Talking about the latency and the bandwidth, we discussed the most commonly used techniques to improve the performance of the main memory. Techniques include the use of wider main memory, simple interleaved memory, and independent memory banks. Then, having discussed the main memory organization, we studied the memory needs to run multiple processors and noticed that it is too expensive to dedicate full address space of the main memory to each of the processor. Then we said that in order to overcome this problem, virtual memory systems has to be used. The virtual memory system allows the use of memory as a cache for the bulk storage, such as the storage on the disk, and it automatically manages the two levels of memory hierarchy, that is the main memory and the secondary storage. We noticed that in order to use the concept of virtual memory, the space on the physical memory and on the disk are divided into equal sized fragments. Here, if the fragment is of fixed size, then it is called a page, and if it is of variable size, it is called a segment. The concept of virtual memory says that the contiguous pages in virtual memory are allocated to different processes, whereas these pages may be either available on the main memory or they may be available on the disk, and at both these locations they may be available at distributed addresses. This you can see from this diagram, which is repeated here again. Then we also introduced the concepts of protection and relocation, and we discussed the importance of these two attributes for the virtual memory. Here we said that the protection against interference of one processor with another is provided by assigning different permissions to each section of the address space and prohibiting the user processors to access the privileged information. Whereas the concept of relocation allows to place a program anywhere in the physical memory or the disk just by changing the mapping between them. Then we discussed several similarities and dissimilarities in the terminologies used for virtual memory and the caches. The terminology page fault or address fault is used in virtual memory system, and it is similar to the miss in a cache. Moreover, the CPU produces virtual address for the virtual memory, and it produces main memory address for the caches. Moreover, the mapping of a virtual memory address to the physical address is performed through a page table in case of virtual memory system. The replacement policies for caches and virtual memory also have some similarities and some dissimilarities. Replacement on the cache miss is controlled by the hardware, whereas the page fault is controlled by the operating system. Moreover, the size of the processor address determines the size of the virtual memory, whereas the cache size is independent of the processor address. Also, the secondary storage is used as a memory as well as a file system where it can provide low-level backing storage for the main memory. Furthermore, we found that the page replacement strategies for virtual memory include FIFO, that is first in, first out strategy, or LRU, that is least recently used method of replacement. However, we said that approximation to the least recently used results in that each page has a reference that is set on a other reference. The operating system periodically resets the reference bit, and when a page is replaced, a page with a reference bit that is not set is chosen. The virtual memory write strategies may include either write back strategy or write through strategy. However, the write through strategy cannot be used for virtual memory system because it has got too long access to the disk, which may result in a very high penalty. The write buffer would be needed in this case to be excessively large, which may not be possible to design. And the I/O system may need an extremely high bandwidth. Again, it may be a bottleneck for the design of virtual memory using write-through strategy. After this, we also talked about the working of virtual memory, and here we noticed that the complete sequence is that the CPU generates the virtual address, operating system manages a lookup table. This lookup table is also known as the page table. The lookup table contains the location of the page or of the segment on the disk or in the main memory. And the hardware converts the virtual address to the physical address through the operating system, which manages the lookup table or say the page table. Here, in case the page fault occurs, that is, when the page table entry indicates that the virtual address is not in the main memory, then the following steps are taken. Number one, the operating system got the full control over the placement. Number two, the operating system exception handler is invoked to move the data from the disk to the main memory. Number three, the current process suspends and others can resume. Number four, the data is to be to the main memory by the operating system. And last, the contents of the page table are updated. Now, with this much understanding of what is a virtual memory system, how it handles the page faults, let us understand the virtual memory address translation concept in detail. Assume that the virtual address space V comprises a set of n pages. That is, it can be written as V is a set of pages addressed as 0, 1 up to n minus 1. And the physical address space P comprises a set of m pages which can be expressed as P is a set of pages 0, 1 up to m minus 1. In this case, m, the number of pages in the physical address, is always less than n, the virtual address space. Further, assume that n-bit virtual address, m-bit physical address, and p-bit page offset, then the virtual and physical address limits can be defined as the virtual address limit is equal to n, which can be expressed as 2 raised to power small n, where small n is the number of bits in the virtual address. Similarly, the physical address limit can be defined as m is equal to 2 raised to power small m, where small m is the number of bits of the physical address, and the page size can be defined in terms of number of bytes by 2 raised to power p, where this small p is the number of bits which can be used to represent the value of the page offset. Now, for the virtual address translation purposes, both the virtual as well as the physical addresses are divided into 2 fields. These fields are named as the page offset field and page number field. These fields for the virtual address and main memory address are shown in this diagram. Here, note that for address translation purposes, the page offset bits for virtual address do not change, as the page size of the virtual memory as well as of the physical memory are the same, and the address translation mechanism maps the virtual address onto the physical address for hit, or for page fault, it is through the main memory resident page table. Let us have a look onto the page table. Here you can see that the page table is indexed by the virtual page number. Here the column showing the valid bit, it represents whether the required page is in the disk or it is in the main memory. Here you can note that where v bit is equal to 0, it shows that the page is on the disk and the page fault occurs. And when the v bit is equal to 1, this shows that the page is in the main memory and it is a hit. The address translation operation follows 3 steps. The first step is translation, where separate set of page tables per process are allocated, and the virtual page number VPN, it forms the index into the page table, which points to a page table entry. The second step is computing the physical address. In order to compute the physical address, the page table entry provides information about the page. Here, if the valid bit is equal to 1, then the page is in the memory and it uses the physical page number, say ppn, to construct the address. Whereas if the valid bit is equal to 0, then the page is on the disk, that is, the page fault has occurred and it proceeds for the protection checking. Now, as you can see from this diagram, that for protection checking, the access right field, that is the second field on the page entry table, indicates allowable access, such as whether it is read-only, it is read-write, or it is execute-only. The address translation is denied if the user does not have necessary permission and the protection violation fault is identified. In order to completely understand the address translation, let us have a look onto the address translation shown here with the help of a simple example. In this example, let us assume that the virtual address is of 14 bits, the physical address is of 12 bits, and the page size is of 64 bytes. As the page size is of 64 bytes, therefore, the virtual page offset as well as the physical page offset is of 6 bits, whereas the remaining 8 bits in the virtual address are used to identify the virtual page number, and similarly the remaining 6 bits of the physical address are identifying the physical page number. Here you can see sample memory system page table only for the 16 entries, where you can see the entries for virtual page numbers ranging from 00 up to 0F, that is for 16 pages of the virtual memory. And corresponding to this, the entries in the physical page numbers, which shows the location of a particular page onto the main memory. However, where the valid bit is equal to 0, the physical page number is invalid, therefore it is shown by a dash over here. Now, with this much discussion about the address translation, let us see how we can enhance the speed for address translation. We have noticed that the page tables are excessively large and they are usually located on the main memory. Rather, sometimes they may themselves be paged also. It results in high miss penalty because every memory access may be at least twice long. That is, there is one memory access to obtain the physical address, and the second memory access may be to get the data. So this shows that the miss penalty goes very high. Therefore, this miss penalty has to be reduced. Different methods have been proposed to reduce the miss penalty. The most commonly used technique is one where the virtual memory is integrated with the cache. This you can see it from this diagram over here, where you can note that a small cache is included with the main memory. This cache is used to remember the last translation so that the mapping process is skipped if the current reference is to the same page as that was the last one. Now, this special cache that keeps the address translation is referred to as the translation look-aside buffer, and it is abbreviated as TLB, or sometimes it is also written as the translation buffer, that is TB. A translation look-aside buffer maps the virtual page number to the physical page number, and it contains the complete page table entries for small number of pages. The information contained in the translation look-aside buffer is shown over here. Here, the tag holds the portion of the virtual address, and data portion holds a physical page frame number. It also holds the protection field, valid bit, and usually a use bit and dirty bit. Note that the dirty bit means that the corresponding page is dirty, which means that some changes have been made in the contents of this page. Here, you have to note that the changes are made on the page and not in the address translation buffer or in the particular block in the data cache. The fast address translation operation using translation look-aside buffer is shown here in this diagram. The operation can be completed in 4 steps. The first step is that the translation look-aside buffer uses fully associative placement policy. Therefore, the translation begins by sending the virtual address to all the tags, and these tags are marked valid. Second, the type of memory access is checked. It is checked for violation against protection of the information in the translation look-aside buffer. Then it matches the tag, sends the corresponding physical address, and the last step is that the page offset is combined with the physical page frame to form a full physical address. However, it should be noticed that the fast address translation has got number of merits. These merits are that just like any other cache, the translation look-aside buffer can be organized either as a fully associative or set associative or direct mapped. These are different techniques which we have already talked about while talking the caches. Furthermore, translation look-aside buffers are usually small. Typically, they are in the range of 128 to 256 entries, even on very high machines. It also permits fully associative lookup on these machines. And note that most modern range machines usually have small n-way set associative organizations. Now, in order to further explore the details of fast address translation, we will discuss this with the help of an example now. Let us consider hypothetical fast address translation architecture shown here. You can see that it comprises virtual memory, where the virtual memory address is of 64 bits. It comprises the physical address, which is of 41 bits. The translation look-aside buffer is direct mapped with 256 entries, and there are two caches. One is at level 1 and the other is at level 2. The level 1 cache is of 8K entries, and it is direct mapped, where the block size is of 64 byte. And the level 2 cache is also direct mapped. It is of size 4 M byte, and here also the block size is of 64 byte. You can note it from this diagram of the hypothetical architecture that there are two simplifications which have been used. Number one, we are using only one level 1 cache, and secondly, as we have just specified in the assumptions, that these caches are using direct mapping. However, in practical situation, when there are two L1 caches, the top half of this diagram is to be duplicated, which will lead to the two translation look-aside buffers. In these two translation look-aside buffers, one cache and one translation look-aside buffer is for instructions, and the other are for the data. Furthermore, here we are assuming direct mapping, and when the n-way set associative caches are used, then each set of tag memory, comparator, and data is to be replicated n ways. That is, for n ways, all this structure is to be replicated for n times, and it is to be connected by using an n:1 multiplexer, which is used to select a hit. Now let us have a look onto this diagram again and discuss its working. Note here that the 64-bit virtual address is logically divided into virtual page number, represented as VPN, which is equal to 51 bits, and the page offset is of 13 bits, because as we have said earlier, the page size is 8K and it requires 13 bits to address the page. The virtual page number is sent to the translation look-aside buffer to translate it into the physical address. Here it is divided into translation look-aside buffer tag compare address, which is of 43 bits, and translation look-aside buffer index, which is of 8 bits, for direct mapped translation look-aside buffer with 256 entries. The next is that the page offset of 13 bits is divided into two parts. The L1 cache index is of 7 bits, and these are the high 7 bits of the address, and the block offset is of 13 bits. The block offset is of 13 bits because there is a 64-byte block which we are using in this example. Now here it performs some comparison, and it checks that if the translation look-aside buffer matches or not. If it matches, then it is a hit operation. As a result of this, the physical page number is sent to the L1 cache tag to check for a match. Now, if it is a match, then we say that L1 cache hit occurs and the block offset selects the word and it sends the word to the CPU. Whereas in case it is a cache miss, then the physical address is used to try the level 2 cache. Now, in this case, when it was a level 1 cache, the physical address of 41 bits is divided into 3 parts. These 3 parts are the L2 tag compare address, which is of 19 bits, the L2 cache index, which is of 16 bits, and the block offset of 6 bits. So the 16 bits of cache index plus the 6 bits of block offset results in a 22-bit address, which is addressing the 4 MB level 2 cache. Now the next step is that the L2 cache tag of 19-bit is compared to the upper part of the physical address. If match occurs, then it is level 2 cache hit and the data is sent to the CPU, which uses the block offset and selects the desired word. Whereas if the match does not occur, then we say that it is L2 cache miss, and the physical address is used to get the block from the main memory. So this example clearly explains how two-level caches are used to work for fast memory translation. Now, with this much discussion onto the fast address translation, let us have some discussion onto the virtual memory protection process. The virtual memory protection process is very important in case of multi-programming, where several programs, which are also known as the processes, are running concurrently and they share the main memory. They switch from one processor to another processor, and for this purpose, some switching mechanism is also included in the system. Here, let us consider an example of two processes, P0 and P1, which are shown here to be sharing the same physical memory. Now, these processes demand that the process 0 must not be allowed to alter the memory of the process 1, and the process 1 demands that it should not allow the processor 0 to alter the memory. And moreover, they should be able to share the pages instead of altering the pages. Here you can see from this diagram the address translation mechanism provides memory protection by using the protection attribute bits for each page. The protection attribute bits are stored in the page table entry and the translation leukocyte buffer. Here, each page gets its own protection, and if a process does not have permission, then it is detected in the address translation and an exception is raised, which is detected during the address translation. In a simple protection mechanism, a pair of registers is used for this purpose. This pair of registers checks every address to be sure that it falls between two limits, that is, a limit of the base and a limit which is referred to as a bound. So this means that the address will be said to be valid if it holds the expression, that is, the address is greater than or equal to the base value or less than or equal to the bound value. And if the user processes are allowed to change the base and the bound registers, then the users cannot be protected from each other. However, note that the operating system may change the register base value or the bound to facilitate the switching between processes when sharing is occurring. Now, an alternative to the base and bound registers mechanism is that we let the processes have their own page table, each pointing to the distinct pages of the memory. However, in this alternative scheme, the user program must be prevented from modifying these tables. Now, with this much discussion, on to the virtual memory, we conclude our discussion on to the three levels of the memory hierarchy. We have noticed that the virtual memories use hardware management and they use separate instructions and data caches which permit simultaneous instruction fetch and data fetch. Moreover, in this discussion, we have been discussing in details the four basic questions regarding the block placement, block identification, block replacement, and write strategy. Then in the virtual memory system, we noticed that virtual memories are software managed and they have very high miss penalty. Therefore, we always want to design them such that the miss rate must be very low. Furthermore, we noticed that the virtual memory system supports program loading, memory protection, and multiprogramming. The use of the virtual memory in multiprogramming we will be discussing in the following set of lectures. We will be discussing the use of virtual memory for multiprogramming and multiprocessing in our following lectures. Now today, to summarize our discussion on the memory system, we will say that we started our discussion from the definition of the memory hierarchy design, where we noticed that different types of memories are organized hierarchically such that the fastest, most expensive, and smallest size memories are placed very close to the processor, rather sometimes inside the processor, whereas the most expensive, slow, and huge memories are placed away from the processor. However, over here we also discussed the design of fast memories such as the static random access memories, and then we have been talking about the dynamic random access memories, and we noticed that the static random access memories are the fastest, so they are used as caches, and the dynamic random access memories are relatively slower, but they are relatively cheaper also. Therefore, they are used as the main memories. However, we also discussed that the increasing gap between the speed of the processor and the storage devices is a motivation for the memory hierarchy design. Then we discussed that the memory hierarchy design is based on the concept of caching and the principle of locality. The principle of locality states that the data or instructions of a program can be obtained by the processor accessing a relatively small portion of the address space at any instant of time. Therefore, it suggests that this space should be available in the fastest memory, which should be closest to the processor. And the principle of locality have got two different aspects, that is the temporal locality and the spatial locality. Then we introduced the concept of caching, and we discussed different options to enhance the performance of a cache. Here we said that the cache performance can be improved by reducing the miss penalty, by reducing the miss rate, by reducing the miss penalty and miss rate via parallelism, and by reducing the hit time in the cache. Following this, we discussed different techniques to implement these concepts to reduce the miss penalty. Here we discussed that we can use multi-level caches, critical word first and early restart. Then we can also use the priority to read misses over write, merging the write buffer, and victim caches. Here we notice that the multiple level caches is more the merrier, which means that the extra people are welcome to come. Whereas the technique such as the critical word first and early restart is intolerance. It suggests that do not wait for the full block to arrive, rather retrieve the word of the block that caused the miss and hence reduce the miss penalty. Where the next technique which we talked about was the priority to read misses over the write misses. This technique can be regarded as a favoritism, as it gives priority to read over the write. Whereas the fourth technique can be regarded as the acquaintance, which suggests merge the write buffer. Here it combines the sequential writes into a single block for fast memory transfer. And the fifth technique, victim cache, is salvage. That is, a small fast memory is added to the cache that recycles the discarded blocks. So to summarize, we can say that in all of this discussion, we discussed 5 methods to reduce the miss penalty, 7 ways to reduce the 3 C's, and 3 methods to reduce the miss rate and miss penalty via parallelism, and 4 techniques to reduce the hit time. Then we talked about the virtual memory, and in the virtual memory we found that the virtual memory in fact uses the main memory as the cache for the disk. Now with this much discussion onto the memory hierarchy, we close the discussion onto the memory hierarchy system design. However, we will continue using this memory system for our future discussions for multi-programming, multiprocessing, and for other usages and other applications in the fast computing system design. Now I stop here and I'll see you next time. Till then, Allah Hafiz.